time. All right, so we are still chatting about natural resources. So lecture D6, this is the 12th Econ of Renewable and part 3. And so we are have been working with this picture of a forest stand. Just as a reminder, you've got your forest stand, so you've got your so you have a privately owned forest. And a forest is a collection of stands so each stand is basically a unit of forest that is uniformly, so you can think of each stand here as uniform in composition, age, etc. And so if we're going to have some stands which are old, and so will be soon to be cut, whereas others are young and some are maybe moderate age. And so when you decide to do a cut on a particular year, then that cut may only affect a fraction of these stands at a time. And so we cut fraction at a time. And what that means then is that even though we have been focusing on managing a single stand, and we're going to start talking about habitat value today, then you might think, well, it seems like weird to focus on habitat value because once you get into old growth forest, if old growth forest is important, you're going to cut the whole thing down. And what happens to anything that's in that habitat? So, how do we deal with that sort of thing? And so the idea is that if you have a privately owned forest, you probably, and there are good economic reasons to do this as well, are not going to cut the whole forest down at a time. You're probably only going to cut sort of sections of it down. And so you might, even though you might cut down one section, there will be adjacent sections that are still growing, and you might cut them in the next year. But the idea is that over the entire forest here, if you have made decisions to maintain old growth forest, then somewhere throughout your entire, all of the stands that go into your forest, then there's going to be some old growth forest. And so it is possible to continuously maintain habitat while also harvesting that habitat for timber. And so, so that's kind of the picture that we have here. So then, the important question then is, how long until we cut a stand? And so we are learning sort of graphical ways to depict that. And so this requires bioeconomic models which capture both the dynamics of the biology as well as the economics of things like the time value of money. And so the, oh, oops. All right, let me do this. Sorry about this. I was adding notes to the wrong lecture, or the wrong spot. So consider this to be a blank page. And I just want to make sure that the notes that I was adding to interesting. Well, I guess I will deal with that another time. Yeah, that's not gonna, all right, well, we'll see. Okay, live theater, huh? So, so the problem that we've been mainly working on here is then if I have a model of, let's say, volume produced over time, that model is probably going to have a period of slow growth, but increasing growth, rapidly increasing after that, slowing, we'll reach a max, and then we'll go into decline. That's kind of a standard way to view that. And so this, you can pick different spots that are candidates for when to cut, like T max, which would be when the change in growth, or you could think of this as, so I should write it maybe this way, where the change in growth over time, the derivative, which I also call V prime, which is similar to just the year-to-year change in growth, is equal to 0. So if you wanted the absolute maximum of volume per stand over a year, then you just wait until the delta V falls all the way to 0. But then we learned that if we actually want to maximize wood production over a long period of time, then we get into the real idea of what a rotation is. And what a rotation is, it means that we invest in a short period of slow growth in order to capitalize on a longer period of fast growth until we start falling into short growth again. And this slow growth out here is really no worse than this slow growth out here. And so if we can, it's better to then position ourselves to be ready to transition into a new period of fast growth. And we do that by cutting. And so by cutting here, then what you're doing is you're forcing the forest back into a portion here, which leads to fast growth again. And thus you have the rotation where you go through slow growth in order to get to fast growth, but when the fast growth falls to a sufficiently low level, then it is time to then go back and reset the problem so that you can get fast growth again. And that's how you maximize growth over a long time period. And if we're just interested in maximizing growth, then we can use this maximum annual increment model, where if we take the tangent to the curve, where it intersects this line which connects to the origin, then that point right there, that's the biological rotation, and TBR is where delta V reaches VT times 1 over T, or VT over T, and this is referred to as the maximum annual increment. And so the slope of this line is the MAI, which is V, in this case, the maximum MAI, and that's the max value. So the slope of that line is always the mean annual increment for any particular policy. And then the maximum MAI happens to be that point right there. And so what we're seeing is that whereas here delta V was equal to 0, so it fell all the way down to 0, then here we're saying delta V doesn't have to fall all the way down to 0. Delta V is going to be equal to this VT over T, which is going to be greater than 0. So we're moving that threshold up. So it's almost as if in order to account for lost opportunity, because that's really what this is up here, this slow growth here is lost opportunity for this down here. And so or another way to view that is cutting early, you might view that this is the lost opportunity. And so in order to account for lost opportunity in the kind of non-renewable case, we had this scarcity rent, which allowed us to stop selling at an earlier point than we would normally sell. And you can kind of think about this as being the same way, is that delta V is kind of like this marginal cost or marginal benefit, depending on your perspective. And in the kind of normal market case, you probably would bring it all the way down to where delta V is equal to 0. So you can think of this as kind of like the normal market case. But when you start accounting for all these future opportunities, then you start paying a type of scarcity rent, which means that your delta V is going to come into equilibrium above 0. And so the question is, how much is enough of that? And so when we introduce the time value of money, which I'm going to introduce down here, so maybe I'll use a different color for that. Then that suggested that we should be focusing not on volume, but on the interest we could be generating if we converted that volume. In other words, we need to really compare. So the time value of money is really saying, how does the growth of VT, which is, by the way, just delta V, compare to the growth at a bank? And so that suggests that what I can do is take this almost the same diagram that I've already drawn. So I'm just going to redraw it down here. And again, I'll put this in terms of volume. But now I'm going to take that V of T and scale it. I'm going to squeeze it by the interest rate. And so if I redraw this V of T, so I'm going to, just to make sure I get things right here, I'm going to draw some dashed lines. Okay, and then so maybe I'll use a light blue for this. I'm going to try to draw the exact same shape of VT, but I'm just going to squeeze it so that it doesn't get as high. And so it'll still hopefully reach that T max at that point there. So if I redraw that line, reaches a max and then comes down and declines, then I'm going to call this R times VT. And this is the kind of growth benchmark for bank interest. So this suggests here that if I plot my delta V function, so if I plot the growth from year to year to year, or if you're more calculus inclined, if I plot the derivative of V of T on this plot, then they'll be able to kind of see all these different benchmarks a little bit more clearly. And so, so if I plot my delta V function, it might look something like this. So I'll plot a delta V function, which maybe I'll try to make this look clean. And it should come down and hit 0 here. All right. And I'm going to make that a little bit different shaped here. Okay, so what I've tried to draw here is something where this is my dv dt, if you prefer, for those of you calculus inclined, which I also call v prime. It's also just equal to the year to year. It's supposed to be a squiggly equals, so the year to year growth. And you notice that this here, it's just the slope. So it's just the slope of the volume curve at every single point. And so you can see that this point here, you just kind of got, we'll call this the maximum growth rate, delta V. And that also corresponds to the maximum growth rate down here of delta V. So we can see that is somewhere up here. And so we can see that our trees start growing, you know, at a respectable rate, but they grow faster and faster, and then they start declining in their speed of growth. And then eventually down here, they hit zero growth. And that happens to be exactly where V of t hits its max. And so from this plot, where I've got my delta V on this axis here, and I've got then my R times V of t over here, then this R times V of t, which is my benchmark, it basically, if I were to sell all of my trees and put them in the bank, this is how much interest would be generated year after year. So you could think of this as yearly interest. From bank. And so what that tells me is that, and unfortunately, it's like right at the biological rotation here, but maybe that ends up helping me. Maybe it's not so terrible, but this sort of suggests, you know, this is at the T Wicksell rotation, that is where delta V is equal to R VT. And so this is, maybe I could say, well, just that's good, I think. And so that is saying that I let my delta V fall, and once it hits the this RVT, that is when I cut. That is my Wicksell rotation. And as I hope you can see here, if I were to increase my interest rate, so increase R or decrease R, then that's going to cause this point to go left or right. So this will be, so just in general, this is what happens when you increase R, and this is what happens when you decrease R. So as the bank becomes a better investment, then you cut your trees sooner, because you can't afford your trees to move into a region of slower growth. And so the Wicksell rotation sort of helps us see that. Now, we then learned about the Faustman rotation, and the Faustman rotation looks identical to the Wicksell rotation. In fact, if I want to be slick here, I can maybe grab the Wicksell rotation curve. And I am going to shift it up just a hair, say to here. And I'll change its color as well to make it clear that it's different. And this new curve here is going to be R VT plus R times the site value minus the replanting cost divided by P minus C. And so I've just taken the Wicksell RVT threshold and added a tiny little bit here, which is just the site value of other things that I could do with the site minus the cost of replanting every year. That ends up being a dollar amount. And then in this case, because I put everything in terms of volume, I divide by this kind of conversion ratio from dollars to wood. So this P minus C is how many dollars I get per unit of wood. And so I'm taking the dollar amount and then dividing it by my conversion ratio to turn it into a volume. And then that gives me an additional volume constraint that I need to meet. And then so that is what makes the Faustman rotation, TFR. And so the Faustman rotation is when delta V is equal to that. That's the Faustman rotation, is when delta V is equal to this threshold right here. Now I want to make a couple of clarifications. There was a question last time about why does S minus D have to be greater than 0, or does it have to be? That's a simplification that I made. In reality, and because I rethought this, the Faustman rotation actually doesn't require, in order for us to do this analysis, we actually do not strictly require that S minus D be greater than 0, but we do require that the net benefit from 1 year is greater than 0. And if I make S minus D greater than 0, I get that requirement. So I kind of said too harshly last time that if S minus D was less than 0, you just wouldn't plant timber. That's not actually the case. It is possible for S to be less than D, or for S minus D to be less than 0. But in order for us to really stay involved in timber, you would be needing to get a lot of benefit out of your trees. And so if the benefit from cutting your trees plus the site value is not adding up to something greater than 0, then you should probably just get out of the timber business. But this is assuming you're in the timber business, and it's saying, given that you're in the timber business, where do you cut? And so that's where this thing comes from right here. And so this S site value, and so I could maybe on the next page here, I'll just remind us what each one of these things are. So P is the price of timber. C is the cost of cutting timber. And so P minus C is the net benefit of timber. And then we have R, of course, is our interest rate or discount rate. S is the site value, which is the value of all other uses for the land, not the timber, like parking lots, etc. And then D is the cost of replanting after a cut. And so when we take all those together, when we think about our balance sheet at the end of the year, and you could say, like, what is our what are our natural asset balance at the end of the year? At end of, I could say, a cutting year. And that is going to be the we can view it as P minus C times the volume that we've cut. And then we can then add, but we have to then consider then that we then need to replant. So then we're going to subtract off the D. So this right here is the net benefit of cutting. But then the land is holding value because that land is an asset that we own. At any time, we could sell that land. So it's like dollars in the bank. It's like principal that is sitting in your bank account, just sitting there. At any time, you could take that principal out and do something with it. But you're not, but you still have to account for the fact that you own that amount of money. And so then you add to that the site value. And I'll say held in the land. It's like principal in a bank account. And so those are at the balance sheet at the end of a cutting year. And so really what the Faustman rotation is saying is that if you took that entire balance sheet and you converted that into dollars, then at the bank, you could earn, maybe I'll put it on the other side. So at the bank, you could take all of that and then you could earn an interest of R times that. So this whole formula here, so this whole formula, including the R, is the potential interest from a bank. That term right there. So I could even maybe highlight that. Well, that's going to change the color of a lot of things. So, well, hopefully that's clear. Maybe I'll see if I can manage to just color. All right, so that's the potential interest you get from the bank. And so we need to say, is the growth that we could get from that going to be higher than the alternative source of growth we could get, which would be the interest we get from natural growth of the trees? And so if I think about that, then I've got natural growth of the trees. Is delta V from year to year. And so the equivalent in dollars is P minus C times delta V. And so really the Faustman rotation is comparing this P minus C delta V to R times my volume at the end of the year converted into dollars minus how much it costs to actually cut and replant, plus the site value. And so that is basically, if you do a little bit of division here, then that's basically saying, is the interest where, how does the return I get from my trees, if I divide both sides by that big thing on the right, except I leave the R over there. So that's effectively, these are the natural returns. And these are my natural assets, which is like your principal. and this is my benchmark interest rate. And at the point where the delta V gets so small that the returns you get over here are less than the returns you'd get from a bank, then that tells you that it's time to cut. And so the no arbitrage condition is basically engineering your cutting strategy so that you get the same interest rate in both cases. So in that case, it doesn't matter if you're putting your assets in the bank or you're putting them in the trees, but it's a nice balance where if you'd like to think of it in terms of rotation, what you're really doing is you're climbing up that volume curve, which I kind of drew up there. So this is our volume curve that you're climbing up there, and you're getting up to a point of fast growth. And at that point right there, you convert those that wood into bank interest, and it then can continue to grow in the bank at the bank's interest rate, at the constant interest rate. Meanwhile, back in the trees, you get to hop on a higher interest rate again. So you're constantly converting wood at just the right moment to grab it when it is not growing as fast as it could in the bank in the natural system, and you put it in the bank so that it grows, and it's frozen at growing at the bank interest rate. And then you generate new income by regrowing new trees, which grow faster than they could grow at the bank. And then once you generate new revenue opportunity that stops growing faster than the bank outside the bank, you move it over to the bank and let it keep growing in the bank, and over again. That is what the rotation is doing. And this is what the Faustman rotation is doing. And you can write it in this way. And I think this is the way that the book writes it. I don't like looking at it in this way. I would slightly prefer taking this P minus C and dividing the numerator and denominator by it. So it would go away here and here, and then would go underneath that thing. But the way I've been presenting it to you is purely in terms of volume units, where I say is the delta V, how does it compare to the interest rate times the volume of trees, and then I've done S minus D. I've just switched the order of those divided by P minus C. And so this, to me, when these are equal, then that condition is the Faustman rotation. And so this is, whereas these are kind of in dollar units, so dollars divided by dollars, then down here, these are in volume units, but it's the same condition. And that's where we've been so far. So are there any questions about that, which we've also called TFR? And does it make sense, this idea of the land holding value? It's just like if you had $1,000 in the bank and you got 20 bucks in interest, you would evaluate that bank very different than if you had $1 million in the bank and got $20 in interest. So that's basically what's happening here, is that the forest owner will evaluate her returns from the forest differently if she views her land as being worth a lot more. And so the same growth in the forest can be valued differently based on the alternative things you can do with the land. And that is what is being captured by this ratio. So if for some reason the land becomes more valuable, maybe things come moved in next to it, then what we're going to see is that private landowners are going to start managing that land differently. So when we start thinking about conservation effects, ecological impacts and so on, we need to think about the economic impacts on ecology of things that happen around things. So if someone is saying, what's the economic or what's the ecological impact of, you know, this, what's the ecological impact of putting this shopping mall or something like in this particular area of city? So so that's kind of the, you know, if I picture a map, you know, where I've got you know, this, you know, giant, so I've got a forest over here, you know, that is you know, that will be harvested, you know, it's a harvested woodlot. If next door to the forest, if suddenly, you know, future, then you can have a high value property moves in to otherwise empty area, nearby area, I'll say. In this particular case, you might think the ecological impact would be light because this was already an empty area, nothing was living nearby. And so putting, you know, some sort of development in this area is not going to dislodge any animals, for example. So you think that the ecological impact might be light if you focused on just this area. However, economically, this area that you've put in here is going to change the site value over here. So this will have an impact on, it will increase perhaps the site value of this land over here. And so even if it is still profitable for the timber farmer to continue to farm timber on this particular land, then just the fact, the mere presence of this nearby area will cause the TBR, so TBR will decrease because the site value increased. So there is an economic ecological effect. This is why these are, again, bioeconomic models. And so when you account for the ecological impact of this in your ecological impact statement, your environmental impact statement, you really need to consider these economic effects, because what's going to happen is that something that used to be old growth, so for example, this might go from old growth to new growth. And so that can completely change the biodiversity that is that's in the forest. So this will be, you know, new biodiversity. So, you know, it's a complete turnover. You know, some species that thrive on old growth are not going to be able to thrive. Some species that thrive on new growth will be able to thrive even more. So it does have an impact, even though you're not acting right there. And the impact is economic. The impact is through human behavior, is that this human who's managing this forest will manage the forest differently because there are different alternative possible uses for her forest. She's not actually paving the forest and putting up a parking lot. So, you know, that's, you know, the Joni Mitchell and Counting Crows, you don't actually have to pave the forest and put up a parking lot to make an impact. The fact that you're even thinking about paving the forest causes an impact. And that's something that people don't get, is that human behavior is affected not only by the assets you have, but also by the opportunity costs. And the opportunity cost of you doing something else here, even if you don't do it, will change what you do here. All right, are there questions about that? Does that make it clear? The Faustman rotation, and that's meant to sort of motivate where we're going with this today. So as I scroll ahead in my notes, okay. So, so I hope we see that the patterns that we are expecting here are things like interest rates increase, and we get decrease in rotations. We also have, if the site value increases, we also get a decrease in rotation. Other things, if the cost to replant increases, then you get an increase in rotation length. And then other things like if price of timber, so P, increases, then you get an increase in rotation length.
Professor, I got a question.
Yep.
These factors, are these regarding to the Wicksell rotation or any type of rotation?
Well, the Faustman rotation so far is the most general.
Okay.
So the Faustman rotation embeds the Wicksell. The Faustman is just, so the Wicksell is just where S minus D is equal to 0. So basically, in history, the Wicksell came out first, and then later economists realized that the Wicksell was leaving out the site value, and then the Faustman rotation was meant to correct that. And so as we're trying to account for all of the costs and benefits so that we can really understand why people are doing what they're doing and what the true, what the incentives are and everything like that, then we go to the Faustman. So I gave you the Wicksell just to build up to the Faustman, but the Faustman is sort of the truer thing. And in the Faustman, it all has to do with this offset. And so the Faustman offset is this interest rate times S minus D over P minus C. And so what this does, this you can think of as being proportional to rotation length. It's not actually proportional to, but it's it moves in the same direction. So if interest rate, or I could say inversely proportional, I'm sorry, I should have said inversely proportional. So I'm going to erase that and say, I'll just write it maybe. Inversely proportional to rotation length. I'll shift this over. And so with that, you can see that if anything causes this to increase, rotation length will decrease. If anything causes this to decrease, rotation length will increase. So they do the opposite thing. All right, so any questions about that?
Oh, one more, sorry.
Yep.
So you just said that if that entire formula increases, the rotation length will do the opposite?
Right.
Okay.
Right. So anything that causes this to increase will lead to decrease in rotation, and vice versa. Any other questions? All right. So if we're interested in social efficiency, and we're thinking about, this hypothetical situation that I drew over here with the harvested lot, the forest that's over here, and stuff that's going on here, then it seems like we're still missing something really important, at least in accounting for the negative impacts of the farmer's decisions. And that has to do with the non-timber benefits of the forest itself. So we've talked about the site value, which is the benefits of the land itself to other humans, or to you and other humans. But what about the non-timber benefits of the forest itself? In other words, what are the benefits to ecology, for example, or to other humans of actually having forests that don't have to do with cutting the forest down and selling the wood? So that's what we need to model in now. And so by modeling those, it suggests ways for us to internalize negative externalities. And it also suggests that, I mean, it's kind of the same thing, that not only negative, it's just ways for us to, if you were to somehow monetize these benefits, then it suggests how it would have an effect on the farming decisions. Then the flip side of that was to sort of say, if you didn't monetize these benefits, it helps us kind of help characterize sort of where dead weight is being generated in this system. All right, so the non-timber benefits. And so the idea is that, let's say, for example, could be recreational value, for example. People like to jog, camp, etc. in forest, and maybe in specifically old growth forest. So they like walking around with, large trees and those sorts of things. So that's something that might be important to humans. But you can also have other, non-human animal benefits that can vary from new growth to old growth. So, for example, you might have, there might be, white-tailed deer thrive in new growth forest. And that's because they maybe like shorter trees where, for herbivory, a large terrestrial herbivorous ungulate like a white-tailed deer needs access to that herbivory. So the new growth forest might be better for the white-tailed deer. So if we want to support white-tailed deer populations, then maybe it'll be important to support young forests. But on the other hand, there might be a particular woodpecker, for example, and it could be an endangered woodpecker, perhaps. And it thrives in old growth forest because that particular woodpecker or flicker or whatever you like really needs to be in hardwood trees, potentially infested by insects and sap. And so it really likes old growth forests that it can sink its little beak into. And so, so if we're trying to support the woodpecker as opposed to the white-tailed deer, then we have a very different management strategy. So there are some complex trade-offs here, obviously, to worry about. So, so so then we have to sort of say, well, then what is the true value? So let's say we're going to focus on, so we could ask people like, you could do a contingent valuation. Where you have surveys and you ask people things like, what are you willing to pay for one species, or species X versus Y. So these are ways that we can help quantify what people's marginal benefit. So this helps quantify the marginal benefit of different protection plans. That is one way to sort of put a dollar amount on what it costs to maintain a particular bird population. And there are other things you could do too. So you could actually, instead of just contingent valuation, you could actually charge people. So you could charge for entry to forest. So, in the book a couple of chapters ago, it talked about how some people value aspects of the environment that they will never actually experience, whereas others will actually value parts of the environment that they directly experience. And so in this case, if someone actually wants to go to a forest where they can see the woodpecker and they're willing to pay for access of that, then you can actually charge them for that. So you can get a true return on there being woodpeckers in the forest, on the forest being an old growth. So either way, it is theoretically possible to account for the monetary, so in dollar terms, benefits of timber, of not timber, of forest. So I'll say the monetary non-timber. So in theory, we could do that. And so what I'm going to do is I'm going to introduce a new quantity called H. And this H quantity is going to be that. So we have done some sort of assessment where we have this is the dollar value of non-timber benefits. And it might be easier for us to focus on specifically old growth non-timber benefits for simplicity. In which case you could think about, we've maybe tallied up all the different values, and it turns out that that all of the values kind of skewed towards old growth forest or something like that. So then how do we model that? Well, what we can kind of think of this in terms of a marginal cost and marginal benefit of harvesting. And so we know that the marginal benefit of harvesting, that's easy. So the marginal, and I'm writing this on the right-hand side of the page, so I can write something else on the left-hand side of the page. So the marginal benefit of harvest, that is going to be and I'm going to scale it by the interest rate here, but it's going to be my volume of trees cut at the time of harvest, which I'm calling T0, multiplied by the net benefit per volume, plus this S minus D quantity, which is my site value minus the amount that I had to replant. So that is how much benefit I'm going to get out of a harvest. And then the kind of marginal benefit is well, you know, I think about, I cut it all down, I put it in the bank, and this is the interest that I make out of the bank. But there is a marginal cost of harvest as well. And so the marginal cost of harvest, we've already been working with effectively most of this quantity, where that is going to be the amount of growth I can get between this year and next year times, you know, converted into dollars times the net benefit per unit wood or volume wood, plus these non-timber benefits. And so this here is the dollars lost to harvesting from growth foregone. I'm not trying to talk like Yoda, I'm just thinking in perhaps not fast enough. And then the H here these are the lost benefits from the forest. So these are non-timber benefits. And so in other words, if I cut the forest down, then I can't charge access to that. So suddenly I lose those benefits. So if I allow the forest to keep growing, I get to keep the H. If I cut the forest down, I kill the H. And so if I compare these two, then I basically cut or harvest when the left side is less than the right side. So this is my harvest rule. So at the instant that my growth shrinks, even with so I'm just incrementing the growth that I was worried about before by this H value. So this buys me a little bit of extra time, but eventually my growth will eventually shrink to the point where the little bit of growth that I have left between this year and next year is small, and the H value is not big enough to dominate what I could be making if I cut and put it at the bank. And so in that case, I take my marginal benefits over my marginal costs, and that suggests that I harvest. So this is kind of the Faustman rotation when you fully incorporate into it the non-timber benefits as well. And if I want to see what that looks like graphically, then all I'm going to do is going to take this whole expression and I'm going to divide it by P minus C. And that will put me back in my volume units that I've been happy to work in. So if I do that over here, then if I rewrite that rule, so this is the volume version. And that volume version of the rule is going to be the delta V plus the dollar value of the forest converted back into volume units by dividing by the cost of wood. And then that is going to be less than the interest rate times the volume at that particular time, plus the interest rate times S minus D over P minus C, again, to convert dollars back into wood. And then this looks just like the Faustman rotation. It kind of shows how this thing's going to work. So underneath it, I can actually redraw my graph that we've been working with. Oh, let me do that cleanly. So these are going to be in volume units. So I will first draw my R times VT. So this will be like my VT curve, but scaled down by R. So that went up, fast growth, peak, decline. So this here is R times V of t. Actually, I'm going to squeeze that down a little bit smaller so that I've got more room. So that right there is like the Wicksell rotation, R times V of t. And then I will draw my delta V curve, and I'm going to make sure that my delta V curve hits 0 right here where that RVT hits its max. And so that looks something like this. And so roughly, if I drew this, right, then I get the max growth rate here. So this here is the max growth rate. And this right here is my dv dt, or v prime, or delta v. And that corresponds to whatever the max growth rate is down here. So I'm not going to, because I'm just hand drawing this, I'm not going to point it out because it's probably not quite right, but you kind of get the rough qualitative idea. And so now I need to add on. So if I want to add the Faustman rotation onto this, then I take, maybe I'll do it in green. I'm going to take this same line and shift it up just a hair. And instead I'll do that in green. And so this here is RVT plus RS minus D over P minus C. So basically this distance here, that is this thing. It's just been shifted up by that much. But then how do I manage my old growth? Well, let's assume here that H at some point, like let's say after the max growth, so right around here, we're going to say that H is basically 0 here. And we're going to say that H increases over time in this region. So at this point, H is equal to 0. And so if I then add on the H to the delta V, then I get this sort of tail thing. So let's say it starts here, and I'm going to make it go down to like that, do that. And so this purple curve is the delta V plus H scaled by the cost of the timber. And so what that shows me is this here is my Wicksell rotation. When I add in all of those other economic factors of site value, then I get the Faustman rotation. But then if I add in the non-timber benefits, then it shifts me the other direction back closer to the Wicksell. And so this right here is this, I guess I could call it Faustman with, I'll just say with non-timber benefits. So we shifted adding opportunity costs up until this point has been shifting the rotation to the left. But when then you properly account for the opportunity costs of non-timber benefits, it shifts things back out to the right. And so you end up getting, if you do not internalize this H. So remember that the actual rotation length depends on whether H is internalized. by timber farmer. So we view, so this is really a question of incomplete markets. And negative externalities. So I'm not going to draw a market diagram to sort of highlight exactly where the deadweight loss is, but I'm hoping that at this point you can see that if a farmer, a timber farmer, does not have these non-timber benefits in mind, then they will make cutting decisions that impose a cost on other possible consumers of that forest. And so that cost is not felt by the farmer, it's felt by someone else. And that negative externality leads to the farmer cutting early as compared to the socially efficient way to cut. So the socially efficient cut would be to cut later and maintain old growth forest in the large forest stand. But the incomplete market, so the market that's generating deadweight loss, will be the one where they cut earlier, maintaining a portfolio of forest stands that are all young growth, that's going to get rid of the old growth benefits. And that will remove these old growth benefits from society. And that means that the deadweight loss is going to be characterized by these lost old growth benefits. Now, if you can internalize that by, let's say, giving the farmer, so ways to internalize. So how to internalize. These H, so this is habitat value. Or non-timber benefits. Well, you know, if there is some way, there might be a market for, you know, there might be a market for charging for entry to the forest. So if there are enough people around that benefit from the non-timber benefits, then the farmer can actually charge those people to say, if you want to keep this forest, you got to pay me. So we're going to get into, this relates to a topic that's going to come up in the next couple of chapters of this Coasean bargaining. And we haven't talked about this yet, and so this is just foreshadowing. And so basically, those who appreciate the non-timber benefits can pay farmer to maintain them. And then the farmer will then now feel that if I cut it, they're not going to pay me. If I leave them up, they will. And you know, you could view this as admission fees to forest, to access forest. That's one way you could think about it. Or you could have the government step in and do something similar. So you can actually have the government pay farmer subsidies not to farm. And this shifts costs from taxpayers to farmer. And so this has an interesting double effect in that if a farmer is already valuing the habitat value internally and keeping their and harvesting much later than their competitors are, then that individual is altruistically paying a punishment. They're not doing what the competitive market would suggest they can do. And what this does is compensate that farmer for being the, so you can view this as in two ways, is either compensation for the this is like in the public radio case. So compensation for providing public good. That's one way to view it, where the farmer is electing on their own to effectively pay a cost by not harvesting at the competitive market equilibrium level, and instead allowing other people to have access to the forest, providing a public good, the farmer paying the cost and everyone else getting the benefit. And so in this way, you're compensating the farmer for the public good. You're forcing the public who's receiving the good through their taxes to pay for the good that they're receiving. So that is one way you're completing the market. The other way you can view this, and both of these can be happening kind of simultaneously, is that you are creating a cost of harvesting early. So by paying farmers who harvest late, what you are implicitly doing is taxing farmers who harvest early. So that would be another way we could have done it, is we could tax farmers who harvest early. That would be a more overt way to put a tax on farmers who are not doing the behavior that we want them to do. But a more covert way to do that is we give a benefit to farmers who do what we want. So we pay the farmers to do what they want, and that implicitly has the exact same effect of taxing farmers who don't do what we want. And so both of those cases is you're effectively making a farmer pay for the negative externality that they're causing. So if harvesting early causes a negative externality, somebody needs to pay for it if we want to get back to the socially efficient equilibrium. And so we can ask the farmers to pay for it. And they either pay for it by directly being taxed, or those who automatically do it get paid a benefit for doing it. And that effectively creates a kind of tax on those who don't do it. And so those who don't, or those who continue to harvest early, now have to pay a cost. And that helps us shift us back towards the socially efficient equilibrium. So that's how we can internalize habitat value. All right. So are there additional questions that about that before we introduce the next topic, which is totally separate from forest dynamics? Anybody? As I open up my next set of lecture notes. Okay. All right, I guess I'll mention, since I was foreshadowing, again, this is going to come up a little bit later, but there are sort of two philosophies for correcting negative externalities. And again, we will talk about these in more detail in the last unit, Unit E, but these are the Pigouvian approach and the Coasean approach, named after, again, some old white guys, some old economists. And the Pigouvian approach is that you tax those who generate damages. And the Coasean approach is government stays out of it, and those who hold property rights can can bargain with others to compensate for damages. And so the idea here is that in the Coasean approach, that if there's pollution that is coming into a town, then you could have that if the property rights for the town are well maintained. Oh shoot, we did. I'm sorry. Well, in this case, it's an excellent time to stop. So this is 118. In my head, I was going to 130, and that's why I was adding the bonus. I apologize for that. So let's do a quick attendance exercise. And the attendance exercise today is, what time is the class supposed to actually stop? So thanks for mentioning that. And I apologize. Again, I thought I had bonus time because I was in my head for my previous class. That's all I've got, so I'm happy to stick around for anybody who has questions. Otherwise, feel free to head out. Again, very sorry that in my head I was going to 1:30. And have a good weekend. See you all next week.
Thanks so much, Dr. Pavlik. Have a great weekend.
You too.